Hello everybody, this is the third video for Chapter 9 of the Reinforcement Learning course. So Chapter 9 was about introducing approximation methods within reinforcement learning algorithms because for problems where the state space is way too large to store one estimate per state for the value function, we need other methods to make the algorithms applicable. So instead of having a separate estimate for the value of each state, what we use in this chapter is a parametric representation of the value function where we instead estimate the parameters of the parametric function. So in the earlier part of the chapter, we discussed gradient methods to estimate the values of parameters. But now in what remains of the chapter, we will discuss several candidates for functions or classes of functions that could approximate the value function. Okay, so this is what we'll do. We'll go through several of them. The first that we propose is called state aggregation. Okay, so we have here, this is our approximated value function at any state st for a fixed policy pi. So in this chapter, one more thing, we considered the fixed policy and we did do on policy evaluation. Okay, so in this case, for that fixed policy pi, the estimated value of the value function is some parametric function of parameters w. So the first family of functions here that we're going to propose are functions that are worth sets of functions that are worth either 0 or 1 depending on which states we are. Okay, so and these will be basic building blocks for state aggregation. So in the state aggregation approach, what we assume is that our approximation entails that we regroup sets of states together, and for any state within a given subset of state, the value function is the same. Okay, so what we assume here is that for similar states, there's a single value which applies for all these states. So this is state aggregations. We aggregate sets of state together, and for all states within the set or the aggregate, then we assume they share the same value. So the value function for all these states is the same. So this entails setting the approximate value function is the sum across all D aggregates. So, okay, before maybe I'll explain that. So we start by taking the state space S and we divide it into a partition S1 until St. Okay, so that we partition the various states. So every state in the set of all states fits within one of the D aggregates or D clusters. And then what we assume in state aggregation is that the approximated value function is the sum across all aggregates of Wj. So Wj is the estimated value for the jth aggregate times an indicator function which is 1 if the states fall into the jth aggregate or 0 otherwise. Okay, so in this approximation we have that all sets in the first subset S1 have an approximated value of W1. All sets in state S2 in the subset of states S2 have an approximated value W2, etc. until in the dth subset of the partition all states within have an approximated value of WD. So the gradient for this function is pretty simple to calculate. So because this is a linear combinations of the w's, then the gradient of the value function in a given state st for a given set of weights w is simply a vector which contains the indicator function. So first element is an indicator which is 1 if we are in state S1 and subset of or aggregate S1. Second element is an indicator which is worth 1 if and only if we're in aggregate S2, etc. until the last element, which is worth 1 if the current state is in the subset ST. Okay, so in this case, what happens is, because recall that in the update formula, maybe we could go here. So this was a particular example. Okay, so this was our update formula for the semi-gradient approach, and we see that the next estimate is the previous estimate plus here kind of update term which multiplies the gradient here. So if we go back to where we were, we see that for any state the gradient is worth the value of the gradient is 0, 0, 0, 0, 1, 0, 0, 0, 0, where the 1 corresponds to the aggregate in which the state ST falls. So that means that whenever we do an update in the semi-gradient method, if the current state ST falls in aggregate J, then we're going to update the value of all states in aggregate G, and then all the value of all other states will remain the same whenever we make an update. Okay, so every time we fall into a new state, we update values for a single aggregate and leave the others untouched. So this might be fine for some problems, but sometimes having like these let's say constant values among states within an aggregate is too simplistic. Okay, it might work well in some problems, and some other it might not work that well. So another approach that some people have proposed is to use linear functions as a parametric representation, but not linear functions of the states, but rather linear functions of what we're going to call features of the states, which are some characteristics extracted from the state. Okay, so here in this linear approach, there are two steps. So first, what we do is for a given state, we have to determine a mapping X. So the mapping X takes a state as an input and returns as an output x1s until xds, where each of these xj's, they represent a characteristic of the state. Okay, so each xi is a mapping which takes the state and returns a real number which is associated with some characteristic of that state. So for example, if you try to make a robot walk, the state itself can be very complicated because there are many body parts in a robot, but you could, for instance, consider first characteristic could be the right arm's position or the height of the right arm. X2 could be the height of the left arm. X3 the height of the left knee or whatever, and X4 the height of the right knee or something like that. So based on these information, we can construct a feature vector associated with the state. Okay, so X is some mapping which extracts partial information from that state. Okay, so here XS contains all these characteristics of that state. And so in that case, we're going to assume that we consider a parameter vector W, which has the same dimension than XS. And then we're going to form the following approximation. We're going to assume that the estimated value function for a given state S, when the parameters are the vector W, is the following linear combination of the features of that state. Okay, so here this vectorial product is in fact the sum of all weights or all parameters within the vectors times the ith feature or characteristic of that state. Okay, so this method assumes that the value function can be expressed as a linear combination of the various characteristics of a state. So again, because of this simple form here, the gradient can be easily computed. Okay, so the value function estimate depends linearly on the various parameters. So if we check this form, then it's clear that the gradient is the vector x itself. Okay, so if we differentiate that with respect to W1, the answer is x1s. If we differentiate that with respect to W2, the answer is x2s, etc. So we see that the gradient corresponds to all elements of the vector x. So in that case, the semi-gradient update rule that we derived earlier has, well, it's exactly the same form, but here the gradient can be replaced by the vector of feature x. And of course, this I haven't written it here, but this guy is simply the this linear combination, so the linear combination of all features. Okay, so this is a very convenient approach because the gradient in that case is not cumbersome at all to compute. But now the hard part in that context would be to determine what would be suitable features. So a typical choice, it's not the only possible choice, but a typical choice consists in considering basis functions. So sometimes when we have functions within some vector space f, it is possible to express any function in that vector space as a linear combination of other more simple functions. Okay, so there are vector spaces f of vector spaces of function f where any function capital F within the vector space can be expressed as a linear combination, so the sum across all elements I of a sequence fi of constant ai times function ai. So a typical example of this is, let's say f is the set of all continuous function over the compact set 0, 1, let's say, then all continuous functions can be approximated through monomials. Okay, so we can express all continuous functions over a given compact interval as an infinite linear combination of polynomials or even monomials. Okay, so this is a result well known in mathematical theory. So if you do analysis, for example, you can prove these results. So it makes sense to say the idea is the following. So we can think of v hat, the approximated value function. Let's assume it can be approximately represented, or even it can, if we assume it can be represented by some function f. So maybe, okay, let's erase this. So maybe we can say that if the value function can be, for any state s, can be expressed as a function of the state, okay, so here, if the value function can truly be represented as a parametric function of the state, then this often we could form the following approximation. Here, ai fi and if we had an infinity sign here, it would be equal, but sometimes we can put here, let's have this parameter vector here. So we can often approximate, in that case, the value function itself by a finite linear combination of more simple functions. Okay, so function and this basis, we're going to discuss that in the subsequent video. We're not going to cover that fully here, but we could consider, for example, polynomials of the state if we want to consider Taylor expansions, for example, or if we want to consider Fourier expansions of the value function. We could have sines and cosines function here in that linear combination. But the idea here is that the value function is a very complicated, it can be very complicated, but often very complicated functions can be represented as linear combinations of more simple functions if the set of simple functions are a basis of a vector space in which the value function is contained. So in that case, what we could say is that we will okay, no. So here, let's erase the W. I'll just write here like this. So in this case, what we're going to do here is that these coefficients here, they're going to play the role of Wi here. Okay, so to have, if this is the case, to have a proper approximation of the value function, what we're going to do is we're going to try to estimate what are these coefficients AI. And for suitable coefficients AI, we should have a suitable approximation of the value function. Okay, so this is how we're going to proceed. We can proceed to use basis functions. So for example, FIs could be monomials, sines and cosine functions, or other sets of basis wavelets, for example, which can approximate more complicated functions. So, okay, this is exactly repeating what we proposed in the previous slide, but if, for example, the set of states is Rm, so states are points, real numbers in m dimension, and if, for example, we know that the value function is a continuous function over Rm, then we can know many suitable bases of that vector space Rm here. Well, no, f is not Rm, but it's the function of Rm into R. Okay, so here the value function is a function which takes a state as an input, a point in Rm, and outputs the value in R. So in that case, we can find a suitable basis of functions from Rm into R. So for example, m-dimensional polynomials or something like that, and approximate the value function itself through this linear combination. And in practice, we don't have, for computational purposes, we don't have an infinite number of a's, but we only consider a finite number of terms on the right side. Okay, so here in this chapter, we will discuss more specific examples of basis functions subsequently in the chapter, but right now we're gonna leave it general and say we have some basis function, a basis of a set of functions. We have a basis. We have a set of basis function of a vector space f, and we use this set of basis function to represent the value function through the following linear combination. Okay, so applying this concept, we can have the following approximation method. So the value function in a state S can be approximated as a linear combination here of the features of that state, where each of the features are determined by applying one of the basis function into that state. And here the W's here, they play the role of the A here, it's the coefficients in front of the various features or the various basis functions, and these W's are the quantities that we're going to need to determine to obtain a suitable approximation of the value function. Okay, so one reason why this linear approximation is interesting is the simplicity of the calculation of the gradient, but also there are other advantages. So for instance, because of the simple form of the previous linear approximation, there are convergence results which can be obtained. Okay, so linear functions, they're a bit more well behaved than other classes of functions, so it's more favorable to do some mathematical analysis. And it can be shown, for instance, that the stochastic gradient methods, so semi-gradient approaches we've outlined in this chapter, can be shown to converge in some specific cases. Okay, so there are convergence results in the literature for this linear approximation, and according to the textbook, one other result that can be obtained is that there's a single optimum in that case. So previously in the chapter we talked about local optima, where sometimes our estimated parameters, they end up not at the global minimum but at some local minimum. Well, if we have linear approximations, it can be shown that there's a single optimum. So if you fall into a local optimum, then you must be in the global optimum. Okay, so this is very interesting because it says that you cannot find wrong local minimums. If you end up in a minimum, then you know you're in the best possible one. Okay, so single optimum, I've put a footnote here in some very weird, specific cases. We call them degenerate cases. Sometimes there's an infinite set of equally good optima, but even in this case, if you fall into one of the optima, then it's equally good as all others. So this is very good news because we have less optimization problems in that sense, because we can apply, for example, more regular optimization methods. When we fall into a minimum, then we know this is the right spot. Now, other convergence results in this linear approximation case, for the Monte Carlo approaches, so when we use a semi-gradient algorithm that we've shown earlier, when the target is the Monte Carlo 1, so where the target is the return of the whole episode that is simulated, it can be shown that this algorithm converges asymptotically to the global optimum. So to the set of parameters which do minimize our objective function, VE bar, where we recall VE bar represents the mean square error of the value function between the true value function and its approximated value when we weight the various states by the on-policy distribution, or the percentage of times we spend in each state asymptotically. So this is a nice result. So it tells us that under some technical conditions, okay, I've put this bullet point here, technical conditions involve that, again, the learning rate should be reduced through time at a suitable pace according to the usual conditions. So these usual conditions, it's the same one that we've discussed earlier. So the sum of learning rates must diverge, but the sum of their square must converge. Okay, so under that condition, it can be shown that the semi-gradient descent algorithm presented early in this chapter converges if we use the target being the Monte Carlo target, which is the return of the entire episode. And this, again, I haven't checked the proofs myself, but I trust the textbook on this. Okay. So this is great. And why do we have convergence in the Monte Carlo case? It's because we can recall from previous chapters that the Monte Carlo target is unbiased. Okay, the expected value of the target is the value function, the true value function. So in that case, we can show that there's genuine convergence to the correct value. Now, but as we discussed earlier, Monte Carlo targets, they're often very variable for many practical problems. So instead, we could consider a TD0 target. So here the Monte Carlo target, we recall it's GT, which is the sum of all discounted rewards for the remainder of the episode. So this is the Monte Carlo, whereas TD0, the target is RT plus 1 plus gamma times gamma is not, okay, it's just gamma times the bootstrapping term, which is here. Okay, so this is the TD0 target. So we can still apply the semi-gradient descent approach, but when using the TD0 target, and here recall that in this case we assume that this approximated value function is the feature times the vector wt here. Okay, so where we can combine a TD0 target with the linear approximation method for the value function, and in this case we still have some convergence result despite the fact that the target is biased. Okay, so what do we mean here by biased target? We recall that because the value function at the next step is not the true value function, but it's only an approximated value, then the expected target here will not be exactly the value function, but it will be only an approximation, which might be different than 0. Okay, so for this reason, we recall that the TD0 target is a biased estimator because it's only an approximation. Its average is only an approximation of the value function. So in that case, we cannot guarantee that the semi-gradient descent will converge to the true value function, but there exist convergence results which show that in this case the parameters under this algorithm will converge to what we call the TD fixed point, where the TD fixed point is not a local is not the global optimum itself, but it's rather a point that is close to the global optimum. Okay, so this is interesting. If we do some TD0 with the linear approximation to approximate the value function, and with a semi-gradient descent approach, our parameters will converge not to the global optimum of the value function, but to a point near it. And that point, we call it the TD, or temporal difference fixed point. So we will discuss more extensively this TD fixed point in the next slides. Okay, so are there characteristics about that TD fixed point? What do we know about that? So first, is there a way we could determine what that TD fixed point is? So let's do a bit of calculations here. So the first line here is the semi-gradient update rule, where here we use what target? This is the TD0 target. Okay, so we use the TD0 target to update. So recall our semi-gradient update rule is next parameter estimates is the previous estimates plus the learning rate times the target. So this is the TD0 target minus the current estimate of the value function. And here, because we work in the approximation case, we must consider that gradient here, which turns units of value function of parameters into units of value function. Okay, so here we recall that in the linear approximation, this gradient here is simply x, the vector of features of the state S. So we here, just to make the notation more simple, the set of features for state st, we're going to denote it xt. Okay, so to avoid repeating the s's everywhere, xt is just the feature vector in state st. Okay, so the gradient here is just that vector xt. And here, the approximated value functions, we can express them in terms of the feature vector times the vector of parameters. Okay, so here there's a pi missing, but this guy, it can be expressed. Maybe I'll choose a different color. So this guy can be expressed as W transpose xt plus 1. Sorry, yeah, W small t transpose xt plus 1. And here this guy, it's W t transposed times xt. Okay, so here this term involves state in the state st, so the feature vector is xt. This is the state st plus 1, so the feature vector is xt plus 1. And we can make that, so this is how we get to the second line here. And then to go from the second to the third line, we notice the following. So, give me 1 second. Oh yeah. Okay, so here the first thing we can notice is that when we have A and B being column vector, we have A transpose B is equal to B transpose A. Okay, so here we can apply the same rule and say that xt plus 1 or W transpose X here is X transpose W. So here we can do that. And by doing that, we can factor out the W here at the right, and then factor in the xt in this equation. And here, so maybe I'll write this here. So let's take another color, maybe red. So WT transposed xt plus 1 minus, okay, so we can factor this W transpose out. So this is equal to xt plus 1 minus xt transpose WT. Okay, so here this is how we factor this W out. And now before that, what we could do is this xt, because this part here it's a scalar, this xt we can here it's at the right, but because this is a scalar, we can plug the xt at the left. Okay, so a scalar, you could put it before or after the vector. So this is why you could put this, distribute this xt here and here. So this parenthesis becomes RT plus 1 times xt. Okay, sorry, this is a t here. Minus xt, this xt here, times this term. And this term, we can introvert, because of this rule here, we can apply what we have here. And we have obtained that this term becomes xt plus 1 minus xt transpose WT. Okay, so here this is how we get to the last line of the slide. Okay, so this is just reformulating the semi-gradient update rule when we use a linear approximation for the value function. So what happens is, if we do have convergence, eventually the WTs should stabilize around some given value. Okay, and we said that the point towards which the approach converges, if it does converge, is called the TD fixed point. So informally, so we could take this update equation here, and we can take the limit when t goes to infinity on both sides, and call the limiting weight vector the fixed point. Okay, so if W converges, this should converge to the TD fixed point. This should converge to the TD fixed point, and this inside should converge to the TD fixed point too. So here, asymptotically, if we take this equation and replace the W's by the TD fixed point, we have that the TD fixed point should be equal to the TD fixed point plus the learning rate times here. This term here is this term where the W is replaced by the WTD, so the TD fixed point. And here we're going to take, instead of just taking that term, we're going to take an expectation over the on-policy distribution, because in average, over the long run, we're going to face this term, but in proportions being the frequency in which we spend times in each of the various states. Okay, so asymptotically, we should obtain something like that. And now again, it's not fully rigorous because, as we mentioned, the learning rate depends on t and shouldn't be shrunk suitably. Okay, so mathematically, what I just did here is not rigorous, but it's, for our purposes, it's going to be sufficient to understand what happens. So because of that, these fixed points vectors here, they cancel out. This lambda t, we can forget about it. And then we have, this leads to asymptotically the following equality. We have that the vector b minus the vector a times the TD fixed point vector, so the asymptotic value to which the parameter vector will converge, where these vectors a and b don't depend on W, should be equal to 0. Okay, so here, how to see we get this? What are the values of b's and a's? So b's, it's just the expected value of this guy here. So b is the expected value of the reward times the feature vector, this. And a here, it's the expected value of this guy, where the TD fixed point, it's a constant vector. So we can take it out of the expectation and we update this. Okay, so this guy being equal to 0 can be expressed as this equation here, where this guy here, the expectation of this guy is b, and the expectation of this guy is a here. Okay, so we obtain that this entails b minus the TD fixed point should be equal to 0. So how to solve that? The TD fixed point should be a inverse times the vector b, where b and a are provided by these expressions here. Okay, so b is a vector and a is a matrix. So this indicates an expression to which the TD0 algorithm, in the context of linear approximations where we use semi-gradient, will converge. Okay, so we know that when we use semi-gradient approaches, where with a linear approximation of the value function, then the parameters will converge asymptotically, not to the global optimum, but instead to a TD fixed point, and the TD fixed point has this expression here, where matrix A and vector B are given here. Okay, so this is interesting. Now so again, here in this course, we don't spend a lot of time discussing the theory and asymptotic convergence results. We don't prove them. Okay, so this, for a more formal, for a place where you treat these convergence more formally, you'd have to go to references. Okay, but for this this specific algorithm, the textbook provides additional information about the convergence proof of the semi-gradient TD0 algorithm with linear approximations. Okay, so you can go on page 206 of the textbook, read the gray text box text box and get additional information about that. But for our purposes, we'll leave that out of scope. Okay, so it's enriching if you want to look at it, but I don't expect you to do so if you, for example, don't have time to do that. Okay, so now we understand that TD0 semi-gradient within the context of linear approximation converges to the TD fixed point, which is not the optimum of the objective function, but a point near the optimum. But now the question is, how near is that TD fixed point from the global optimum? Then there are results in the literature which provide some answer to this question. So if we have a continuing task, a discounted continuing task, so the discount factor is smaller than 1, and there's no end to the episode, then we can have a bound which characterizes the loss of performance due to convergence to the TD fixed point instead of the global optimum. And this bound says that the objective function, okay, so mean square error of the value function at the TD fixed point should be smaller or equal to 1 over 1 minus gamma, the discount factor, of the true minimum of our objective function. Okay, so for example, let's give an example, if gamma is 0.5, so you have a discount factor of 0.5, then this would be 2. And this guarantees that at the TD fixed point, your mean square error of the value function would be smaller or equal to twice the best possible mean square error you could achieve. So this is great. It bounds the performance loss due to converging to the TD fixed point instead of the true global minimum. Okay, but this term here, we said we must have discounted continuing task. So when gamma approaches 1, so if you have an undiscounted task, then gamma would be equal to 1, or maybe let's say a discounted task but with a discount factor very close to 1, then this guy would be very close to 1, and this whole term here would simply explode. Okay, 1 divided by 0 is infinity. So in that case, when the discount factor is pretty close to 1, the loss of performance can be very large because that bound would be not tight at all. Okay, so if gamma is close to 1, the bound is very large, so convergence to the TD0 fixed point might not provide a good approximation. Okay, but when the discount factor is small, you should have a more satisfactory solution by converging to the TD fixed point. Okay. So recall that if you want to converge to the true global minimum of the objective function, so if you want to get the best possible mean square error of the value function in that context of linear approximation of the value function, you can always use the Monte Carlo approach. Okay, so we said the Monte Carlo approach with semi-gradient converges to the best to the set of parameters providing the best mean square error, whereas if you use a TD0 target instead of Monte Carlo approach in this framework, your parameters will converge not to the best parameters, but to a set of parameters which is not too far away from the best ones. So in practice, which one is preferred? So do you prefer converging to the best parameters, or is this TD fixed point a sufficiently good result for practical purposes? Well, for many applications, despite having having a guarantee of converging to the best possible value, a lot of people prefer the TD0 approach because of advantages we've discussed in earlier chapters. Okay, so for TD0 approaches, the target has much less variability. It's observed much earlier because you don't have to wait for the end of the episode. You can know it on every state, etc. So for this reason, TD0 accelerates convergence, and this acceleration of convergence is often deemed suitable, and some people prefer that at the expense of not converging to the best possible parameters asymptotically. Then we can also, so we could also derive in between algorithms where we don't have Monte Carlo targets or TD0 target, but we could instead consider the target being an n-step TD target where the target sums the next n discounted rewards and then adds gamma to the power n times the bootstrapping term, which approximates the value function in the nth successor state. So in that case, this would be an in-between where the target is not too biased but not too variable, and this could provide better convergence through a more suitable trade-off between bias and variability, as we did before. Okay, so same thing here. If you don't want too much bias and you'd like convergence to a better point, then maybe n-step TD could be preferable to TD0 for the target. Okay, so recall that for this linear approximation case, we just stated that our parameters estimate will converge not to the global optimum of our objective function, the mean square error of the value function, but they will converge instead to the TD fixed point, which can be given by this expression. So the TD fixed point had this representation here. Okay, where here expectation mu entails that the states, okay, so here we don't see the states explicitly, but recall that xt was the set of features evaluated in state st. And here st, in this expectation, st is distributed according to the on-policy distribution, which is the long-term frequency of time spent in each of their respective states. Okay, so now we know the TD fixed point, and we might wonder, well, if we know the value of the TD fixed point, why do we want to apply the TD0 algorithm? Why not directly estimating B and A according to these formulas? So why do we apply a semi-gradient approach? Why not directly simulating many episodes and then estimating directly this vector B and this vector A to get our parameters? Well, this is a very good question, and there's a method that does explicitly that. This method is called the least squares TD method. Okay, so typically the least squares TD method simulates a bunch of episodes, and then across all these episodes, it estimates these expectations by the sample averages of these quantities. Okay, so you can calculate the sample average of rewards times the feature vector, or these. So this is a matrix, but this like kind of matricial product of state vectors. And if you do that, you could get an estimate value of the TD fixed point, which you can use as your parameters to estimate the value function. So as we said, these points here, which characterize the TD fixed point, their expectations. So in practice, we will use sample average to estimate them. So we can estimate the matrix A by AT, which here we use, okay, in theory would be a sample average. Okay, so here, to have a proper estimation of the expectation, we would have a sample average 1 over t times this summation. So this is the, this guy here is the guy that was in the expectation. And in practice, what we do here, a common technique is to use to add the term which is epsilon. So epsilon is a very small constant times the identity matrix. Okay, so why do we add this epsilon term here? It's just to ensure that numerically we don't have problems inverting the matrix. Okay, so sometimes this matrix can be a bit hard to invert if it's not well behaved numerically. So by adding this term on the diagonal, it makes it easier to invert the matrix numerically. Okay, so here I said that we should have 1 over t, but we're not going to put the 1 over t. Let's see why in next. Okay, so let's forget about the 1 over t. And here we can estimate b by the sample average of rewards times the state vectors. If we wanted to have a true average, we should divide over t. But here we won't divide by 1 over t, and we're going to see why in 2 seconds. Okay, so here we had that the TD fixed point, was equal to A inverse times B. Okay, but here this is equal to, we can write this instead. Okay, so TB. Okay, so if we can write this instead, the t here and here, they cancel out, so this expression is equal to this, and this is why in the estimates we don't need to divide by 1 over t on both sides. We can multiply both estimates by t, and we would still get a suitable estimate of the TD fixed point. So here, in that case, for the least squares TD method, the time t estimate of our parameters is simply the inverse of the estimate of A given by this formula times the estimate of B given by this formula. Okay, so and as mentioned, here we don't divide by 1 over t because they would cancel out here and here, so we don't need to put them there. Okay, so this approach where we estimate our parameters throughout this expression is known as the least squares TD method. Okay. Now, what would be painful about this method if we didn't have any additional tricks is that we need to invert the matrix A hat t on every time step t. Okay, so every time there's a new state observed, we get a refined estimate for A and B, and since the TD0 fixed point is provided by this expression, we need at all time steps to invert the matrix A. Okay, so this would be very inconvenient, especially if there are many features. So if the feature space is very large, so recall that we said the feature space is d-dimensional, but if d is quite large, let's say d is equal to 20, then matrix A would be 20 by 20, and inverting that might be quite inconvenient. Okay, so if d is 100, then inverting 100 by 100 matrix is not very fun. So this might be problematic if we wanted to apply the least squares TD approach directly, but fortunately there's a formula called the Sherman-Morrison formula that is proven, that you'll need to prove in the exercises. And the Sherman-Morrison formula allows for a recursive computation of the inverse of A directly. Okay, so you don't have to do a full numerical inversion of the matrix A on every time step. You could use the following recursive formula, which says that the inverse of your matrix A hat at time t plus 1 is your inverse at time t, so your previous step inverse, minus a correcting term here, where this correcting term involves the inverse of the previous matrix, which you've already computed in the previous steps, and then you need to multiply by the feature vectors. But all these are not inversions, they're matrix multiplications. Okay, so it's much easier to multiply matrices or vectors together than inverting a matrix. So computing this term here is much simpler than inverting the matrix A. So this Sherman-Morrison formula makes it easier to use a TD least squares approach in practice. Okay, so this will end up the video here. So in this video, we've discussed two main approaches for the constructor. The two main ways to approximate the value function through two main families of parametric functions that can be used. Okay, the first parametric approximation function was state aggregation, where we assume that various states have approximately the same value function. But as we discussed in practice, sometimes this approximation is too coarse, it's not good enough. So a second approach we suggested is that for each state, we should associate a feature vector to that state representing a few characteristics of that state, and then we can make an approximation of the value function through a linear combination of these features. And we said that we didn't discuss what features we would use. Well, we did a bit, so we said that we could use basis functions, but we didn't have a more thorough discussion about these. So in the next video, we will discuss various ways to select these features. Okay, so if we want to apply a linear approximation where the value function is approximated by a linear combination of features of a state, we need to design suitable features. So the next lecture will be about possible choices to design features of a state. So have a nice day, and I'll see you for the next video next time.